Okay, I think we'll get started. So today we're going to do the first lab in the Machine Learning for General Chemistry Part 2. And this is going to be doing some reinforcement learning to teach a robot how to titrate sodium hydroxide against hydrochloric acid. The key concept that we're working with in this lab is reinforcement learning. So this is the first time we've run into this concept. And in particular, we'll be working with a method called the DQN method, or the Deep Q Network method. I'll say a little bit more about that in just a bit. As kind of an overview, reinforcement learning is sort of like playing a game where you get points for doing well and you get penalties for doing bad, and then as you play the game, you learn what works well, and then you learn what gives you penalties, and you get better and better at that game. That's the same thing that's going to happen here with the computer. And so what we do in a reinforcement scenario is we have some sort of agent. That's going to be the robot that's performing the titration. The environment, so those are the rules that we set up. So add a certain amount of NaOH. You'll see an indicator come up when you get close to the endpoint. It'll get too dark if you're past the endpoint. So those are sort of the environment that the action is being performed in. The performance is always based off of the current state. So the system will evaluate its current state and then what action to take from that state. So the current state is just where we're at so far. So the robot has started and it has added 2 mils of NaOH to the titrant. Okay, then the action is the robot then needs to decide, do I stop adding? Do I increase my flow rate? Do I decrease my flow rate? And so on. So in the ideal case, the robot will learn to have a pretty high flow rate, get the flow rate going, and then turn the flow rate down as we get close to the endpoint, just like we would if we're performing a titration in the lab. And the system is based on a reward and penalty. So if progress is made towards the goal being nailing that endpoint, then you get positive points. And if it is an action such as stopping the flow rate before you're even there or going past the endpoint, then you get penalties for that, and that will reduce the reward. And so again, just like if we were playing a game, we're trying to get the highest score here. Computer's trying to get the highest score in this scenario. Okay, so just a little bit more about this DQN model. It's a combination of a couple of machine learning algorithms, the Q-learning algorithm, and deep neural networks. So the Q-learning algorithm will estimate the possible values of each action given the current state. And then those will be used by the deep neural network to adjust the weights in its network. And in doing this, the neural network then learns it develops the right weights to perform the right actions. In this particular case, the DQN will learn the best action for the robot to get very close to the endpoint, but not go over. So the way I set this up is I put a very severe penalty for going past the endpoint and less severe for not going quite far enough. So you could have set it up differently where you're just an absolute difference from the endpoint. But the rules for this game is more of a penalty to go past the endpoint than to stop a little bit early. But we'll see that the robot will get very close to the endpoint. Now, why would one do this? So you can train a robot on a computer very, very fast, many, many times, compared to the physical setup in the environment. So if you set up a reasonably good physical scenario for the robot, whether it's trying to learn to climb stairs or titrate a reaction, then you can train it in the computer to get a good base for that. And then you put that neural network into the live robot out in the open and then have it perform real titrations. So those are going to be extra environmental factors that it will need to adjust for. So then it can fine tune its learning after that. But you can do a lot of the heavy lifting of that learning by pre-training in a simulated environment on the computer. And that's what we're learning about today. Okay, let's go to the computer, kind of walk through things. Okay, so here's our setup. Hopefully you've got this up on your computer. If you haven't, go back to the first lab in this playlist, or not even lab, but just the introductory video in this playlist to see how to get that all set up on your machine. So we'll be doing the titrating robot here. This is from the manual, so let's we'll go kind of quickly through this because I talked about this on the board here, but we'll be doing reinforcement learning with this DQN network. And what we're trying to do is train this so that in a real life scenario, you could set up the robot to do these titrations in, let's say, a quality control environment or something like that. Talked about the action, the environment, so you can look at that and sort of remind yourself of that, kind of keep track of what's what in this model. Then we have this reward system. So the analogy here would be you say, if you are in general chemistry now or remember back to general chemistry and you're doing your titrations, you're trying to learn how to do them, and you go a little too far and you get well past that endpoint and your indicator turns bright, say pink if you're using phenolphthalein, and you get a disapproving look from your instructor that you didn't quite do it correctly. So that's the penalty. So we get this reward value R, we'll get a minus 100 if we overshoot that equivalence point. Also, if we come to our instructor and say, I think I'm there, and your solution is completely clear, and you've stopped way too soon before the endpoint, then that would also get a disapproving look. So that's, if you stop early, then that's also a penalty for this. Then I won't go into the real details of the process, but just a couple of basic things. We want to stop as close as we can to the equivalence point, so we keep gaining points as we get closer and closer to that equivalence point, and then we would lose 100 if we step over. So gain points, and then we would lose it all if we step over. And then we also want to partly to get the algorithm going, but the robot doesn't know what it's supposed to do, so it's just trying to learn at first. And so we want to give a little reward whenever it steps in the right direction. So when it starts to add titrant, we want to get some reward. So to get it going, we want to add titrant. So there's a piece of the reward function that just has it, that gives it some points for just moving forward in its titration, because it wouldn't know to do that, and that all needs to be built into the reward function. Okay, let's see. We talked a little bit about the DQN network. We obviously aren't going into details. If you want to learn more about that, I encourage you to do so. But we won't talk much more about the details in this lab. I'll talk a little bit more detail though about the training regimen. So I kind of thinking about this as position would be the volume of the titrant that you're, so our position along that volume added line. And then the velocity is how fast we're adding titrant. So when you see the graph here, we're gonna actually see volume of titrant added versus time. Because yes, we could have the robot come to right before the endpoint, but if it takes 3 hours to do that, it's not a very useful thing. So the velocity is important here. Couple of things that are kind of behind the scenes. Just like us, we get a little bit of a warning when we start to get close to the endpoint. The phenolphthalein indicator in this particular case of that would most likely be using, or just the indicator in general, will often start to turn a little bit and then fade away. And then we know we're getting close to that endpoint. So I've built in a little warning for the robot that it is getting close to the endpoint. And then the other thing we often do, and you've maybe done this in when we're taught how to do titrations, is we often do a sacrificial run the first time, because we have no idea how much it's going to take, unless we have some information about, like, it's approximately this concentration or that concentration. But if we absolutely have no idea, then we don't know if we're going to change after 8 milliliters or 24.5 milliliters. So we do a fast one. We go past the endpoint most likely, and then we get an idea of where we should be. So the robot will also get this information of the sacrificial run. So it will know that it needs approximately 16 milliliters, for example. Okay. Just again, a little bit more detail, just to kind of simplify the model of giving the robot just certain things it can do. So it can accelerate by 0.5 milliliters per second, or decelerate milliliters per second squared, or maintain the current velocity. So those are the decisions it has to make at each current state. The decision about the next action would be to turn up or turn down or maintain the flow rate. And then we talked about the reward system here, so I won't go into that. All right, well, let's go run the experiment. And this is what's quite nice, but sometimes not nice about this is it's every time it's different. So the last time when I practiced this, just before this video, it was perfect. It illustrated all the good points. So hopefully that'll happen again for us. But let's go ahead and try this, and you will get something that behaves differently than what I get or what you're seeing on my machine. And that's why we have in this procedure have you do this a couple of times, kind of to get a sense. As often, we need this running in the background here, but you can minimize it. You just don't want to close it, and it takes a while for the program to get going. And I wonder why. Let's see. Oh, there. Okay. Just takes a little while for it to get going. Okay. I'm going to change the number of training to 150, as is told to us in our lab procedure here. That's a pretty good amount. And in fact, I've noticed that sometimes, and it's probably a problem with my reward function, that you can overtrain. And I don't know if that's something that happens regularly, or if it is more of a problem just not getting that reward system tuned just right. So we're going to try 150. This will go relatively slowly. I'll talk, but if it gets to be like we need to pause the video and pick back up, then we'll do that. So we'll go 150, hit start training, and we'll start to see something come up here. And first we see, so here's a good example here. Every fifth one is going to show up, and you'll get the results down here and kind of in visual form. So we can see this is sort of the path it took. So very kind of a slow slope, and didn't do so well. I mean, it stopped a little early. Here, did a little better. You can start to see the color getting closer to that indicator, although stopped still a bit early. Now, as we go, so maybe in some sense this might be good. Sometimes it can get lost, so we'll see if it comes back here. If not, we will start our calculation again. Oh, okay, started to come back. So we should see reasonable. And then these should start getting to be fairly bright, although we don't want to get all the way to this color because that means we're too far. So we're shooting for kind of like this color of our indicator right in here. So about 0.5. And 30 runs. We'll see here we're getting a little bit faster. The slopes are a little steeper, so it's doing it not only getting closer, but it's also doing it better. We've got a bit of a way to go here. So I think what I'll do is I will pause the video now and then pick up maybe when we're on episode 140 or something. Okay, come back a little early. It's getting some really nice runs here. Oh, here's a good example. We just went a bit too far. See, 16.48, and it was supposed to be the true value is 16.47. So then we got a reward of minus 99. So we hit that minus 100 came in. And here we can see stopping a little bit early. So we stopped 14.52, and here's 14.62. So hopefully we'll, although we're getting to the end of our run, we'll see if we can get even a little bit better than that. There's a nice hit there. So 23.45 and 23.46 is what it was supposed to be. And you saw that about the right color of the indicator there. Couple more to go. One more to go. That was a bad one. That went off took way too much time to get there. So it had a negative here. Hopefully that didn't adjust things too badly. Okay, so we're done here. So now what we do is we go save model. And as we look at the notes here, let's see. When we save, we want to save file name .weights. So I have one from the previous run, and we'll look at this as well. But let's do this one here. I'll call that Darren 2 weights. And then you don't need the .h5. That'll automatically put that on there for you. Okay, so now we're ready to evaluate this model. So let's give it an unknown and have it calculate or determine this. So maybe your instructor will give you specific values here, but let's go ahead and just put some in here. So, well, let me load the model. So I'm going to load Darren 2 weights here. That's what we just trained on. And I'm going to go 0.10, let's see, 0.1110 as a concentration of our HCl. We've got, let's say, 16.05 milliliters, and our concentration of our sodium hydroxide is going to be 0.1001. So now the first thing we do is a sacrificial run. So just like we would do in the lab. So this gives us now the true value, and this is our estimated value based on our sacrificial run. So the robot will know this estimated value. And now I want to perform the titration. So let's see how well it does with this training set. Oh, not good. It took too long. Oh, okay. So that training error at the end, the very end that we saw there, seems to have been a bit devastating for this. I'll try just another, I'll just change this. And just change these numbers a little bit, but I'm guessing we'll still have some problems. Yeah, we're running off the edge. So this is a good example of where it failed to train well. Now, let me load a different model, one that did actually train really well. And so this actually turned out to be a pretty good scenario. We kind of saw something that can be a problem with this. And again, I think it's more my reward structures than the stability of the model itself. So I think I've got a new model loaded. So let's just try this now. Sacrificial run, perform the titration, and then pretty good. Look at in the first one, it actually missed a little by less. So this is interesting. The real answer is 13.23, and it got 13.23, but it looks like a little bit more, maybe like 13.235 or something. So there was an error here and it went past, and notice it did go past the value. Now the other values, actually rather poor here. So close, but not as good as we would like, and we can kind of see we didn't quite get there with this color. So let's just try one more run here. Let's go back to that 16 and change this again. And you want to stay reasonably close to 0.1, and then you want to stay somewhere between 10 and 25. You want your endpoint to be somewhere between 10 and 25. Okay. And so close, but we did have one run that went past. And so you can see that this robot has been trained, but it can still, it's not, because this is somewhat just a new scenario for it, it's not absolute. So even when it's trained, it can go past, as we've seen here. But when we look at these, we get very consistent results. And so this is a good example of how this has been trained, but it still can make mistakes. So what you'll do, I won't do this, but what you can do is train it with less runs, see how that does. Could get lucky there and get some good quality runs even though there's less of them, or you could see that the variability will be much greater. So I encourage you to play around with this, explore this a little bit more. And if you're interested in this, dig in a little bit more on what the algorithm is doing and the nature of reinforcement learning and how it's used in chemistry. All right, so that's it for this lab.